Hi everyone. So if you've taken a math class before, you might have heard or seen the number e, which is approximately 2.71828. It is also called Euler's number, and there are many ways that you can define this number. One of the ways can be seen below, and it is if you take those fractions, even the ones that you can't see, and you continue that pattern, there would be infinitely many of these fractions. If you combine them all, take them together, and add them up, even though it seems kind of weird because there's an infinite amount of them, if you add all of them up, it gives you the number e. So example 5 says, using a graphing utility, graph y equals e to the x power. And just think about it for a moment. This is almost like saying y equals 2.71 to the x power. So it's going to look very similar to when we graphed y equals 2 to the x power. So I'm just going to pull up Desmos here, and I've graphed 3 graphs here. And here's the graph of y equals e to the x. And previously we graphed together y equals 2 to the power of x. And notice the blue graph, which represents e to the x, that grows at a faster rate than the other one does, because the other one's doubling, but the blue graph is growing, not doubling, and it's not quite tripling. So let me show you the graph for tripling. That's y equals 3 to the x power. So it's not growing quite as fast as that one, but because our base value, or our b value, is 2.71, it's growing at a rate in between those two graphs. All right. Let's return to our notes. So example 6 says the following table gives the millions of metric tons of carbon dioxide emissions from biomass energy combustion in the US for selected years between 2010 and 2020. Part A says use exponential regression to find a function that models the data above. Now, before I jump into my calculator, I want to use t values. So I'm going to let t represent the number of years after 2010. So if I do that, then these would be 0, 2, 4, 6, 8, and 10. That's going to make it a little bit easier when I punch those into the calculator. So I'm going to come over to my calculator. I'm going to hit the stat button, and then I'm going to go to edit. And here I'm going to enter in my data. So I'll do that really quickly. All right, so I've gone ahead and I have entered in those numbers into my graphing calculator. Then what I'm going to want to do is I'm going to hit Stat and go over to Calc. And previously we've used like the linear regression, the quadratic regression, but today we're going to go down to this option, option 0. It says EXP, and that stands for exponential regression. So I'm going to go ahead and hit Enter and go through the list, and then finally go down to calculate. And there it has given us our function. It gives us our a value and our b value, which is really nice. So our function is, and you can use f of x or f of t, that's fine. I'm going to use f of t equals 108.3877 times 1.2132 to the t power. So part B says use your model from part A to predict the CO2 emissions in the year 2030. 2030 is 20 years after 2010. So for our model, we would want to evaluate f of 20. So that would be, we just take the function from up above. And so I'm just going to throw that into my calculator. Okay, so this is approximately 5171.64. And what does that number represent? So that is millions of metric tons of CO2 emissions. That's a lot. That's a lot of emissions. That's a lot of carbon emissions, and I'm fearful for our planet, but hopefully we can work on some stuff to get those emissions down so that, we can save our planet. All right, example 7 says, Mr. Kwan starts to collect some special kind of bacteria in a petri dish. He starts off with 5 bacteria in a dish, and it doubles every minute. A says, create a function f of t that models the number of bacteria after t minutes. So f of t is equal to, we start off with 5, that's our starting amount, and then our growth rate is 2 because it's doubling every minute. So that is our function there. No need to really do anything else. Part B says use your function from part A to figure out how long it will take for there to be 1 million bacteria in the petri dish. Now, so far in this class, we don't have the algebraic tools to be able to solve that, because normally what we would do is we would set our function equal to 1 million. So I would have 5 times 2 to the t power, and we would have that equal to 1 million. And then we'd solve for our variable t. Right now, our t variable is in the exponent, and I haven't given you the tools to figure out how to get it outside of the exponent so that we can solve for it. So what we could do at this point is you could use your calculator and you could plug in values for t and kind of guess and check. So, maybe you could try t equals 10. So what we would do there then is we would do 5 times 2 to the power of 10. I've thrown that into my calculator, and that is 5,120 bacteria. So that's not quite the number that we want. Again, I could plug in maybe, let's say 15. So I would have 5 times 2 to the 15th power. So I've also plugged that into my calculator. After 15 minutes, there would be 163,840 bacteria, but that's not quite the million that we're looking for. So as you can see, guessing and checking is kind of a pain. At this point, again, I haven't given you the algebraic tool where you could solve that algebraically, so I'd say the next best thing is to look at the graph. So the red graph, you can see the top function is y equals 5 times 2 to the x power, and then the other graph is y equals 1 million, because basically we can set them equal to each other and solve for their intersection point. And we can see here, the intersection happens when the input value is 17.61. So what that means in the context of our problem is that it would take approximately 17.61 minutes for their, oops, wrong there, to be 1 million bacteria. Stick around for the next unit, because in the next unit, I will show you the tools to be able to solve this without having to guess and check, because that is very time consuming. So stick around and watch videos from our next section.